Okay, this is the homework for Statistics Lecture 1, creating a frequency table, relative frequency table distribution. Question 1 corresponds to how many cups of coffee somebody is drinking. So let's take a look here at how we can gather this data. If I want to count the number of data values that consisted of 0, okay, I'm going to count how many zeros that showed up here so I could determine the frequency. Of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There were 10 zeros that showed up in this frequency. Well, I should say the frequency of the data value 0 is 10. That means 10 people drank no coffee. Let's count the data values that are 1. 1, 2, 3, 4, 5. 5 data values consist of people saying they drank 1 cup of coffee per day. So 5 students said they drink 1 cup of coffee. Let's count how many students drink 2 cups. 1, 2, 3, 4, 5, 6, 6 students drink 2 cups of coffee per day. How many students drink 3 cups? 1, 2, 3, 4, 5. How many students drink 4 cups? 1, 2, 3, 4, 5, 6, 7, 8. So 8 students say they drank 4 cups of coffee. Now let's double check that data value 2 here, and we say 1, 2, 3, 4, 5. Sure enough, that's 6. Okay, if we scan through this, we're going to find that it looks like every data value here is accounted for. So we organize this in terms of a frequency table, and we determine the frequencies of every data value. Now the data here represents, like we said, this is the number of cups of coffee a person drinks per day. And I think it's a student sample, so we're talking students here. Let's find the relative frequency. Now, relative frequency, again, let's remember, is a frequency divided by the sample size. And the sample size can be determined by taking the sum of the frequencies or by counting your data that you have here. So you can count the number of data values, but a very simple way is going to simply be to sum my frequencies, add all of these values. Okay? So when we do that, let's sum the frequencies. We find that 10 plus 5 plus 6 plus 5 plus 8. 10 plus 5 here is 15, plus 6 is 21, plus 5 is 26, plus 8 is 34. Our sample size here is 34. We have 34 data values. So our first relative frequency value is going to be 10 over 34, 5 over 34, 6 over 34, 5 over 34, and 8 over 34. These are my relative frequencies. However, they wanted us to compute or approximate our relative frequencies to the nearest thousandths position. So the thousandths is actually 3 decimal places. So we're going to look at all these relative frequency values, like for instance 10 over 34. Looking at our calculator, 10 over 34 is going to give us a decimal value. 10 divided by 34, we get is 0.2941. Now this 4 is in the thousands position, and we look at the digit to the right. Since it's a 1, we just simply know that 10 over 34 is going to be really 0.294. So I got to replace this fraction here with 0.294. That's going to be our first relative frequency value approximated to the nearest thousandths. That means 29.4 as a percent. Right, these are our percents of the sample drink no coffee, 0 cups of coffee per day. Since this is what this is about, it's about drinking coffee in this homework question. It's about 29.4%. Now, for the next relative frequency, 5 over 34, we'll see what this is going to be. And I get 0.1470. The 7 is in the thousands position. I look at the digit to the right. It's a 0. Since it's a 0, we forget about it and we don't change the 7. So 5 over 34 as a relative frequency, as a decimal, becomes 0.147, which means 14.7% of the sample drink 1 cup of coffee. 1 cup of coffee. Okay. Let's look at this 6 over 34 relative frequency value. We get 0.17646. 6 is in the thousands position. The digit to the right's a 4. That means leave the 6 alone. 6 over 34 as a relative frequency becomes 0.176. Now, since we already did 5 over 34, let's first put this as a percent. We know this is actually 14.7% because we did that already in a prior relative frequency. So what we're seeing here is that 17.6% of the sample drink drink 2 cups of coffee. 14.7% drink exactly 3 cups of coffee. We just now need the 8 over 34. And let's determine what this will be. And we get 0.2352. So the 5 is in the thousands position. That 2 says don't change anything. So it's 0.235. So I get 0.235, which is 23.5%. So 23.5% of the sample drinks exactly 4 cups of coffee. So this is the kind of scratch work we can do when we actually want to create a frequency table and a relative frequency table. This is what it would look like, and we're now going to try to answer all the remaining questions here. So let me erase this here and go through how we can try to answer the next set of questions. They want to know. Question B is, what percent of the sample drinks at least 1 cup of coffee per day? So, what percent, let's write this down. What percent of the sample drinks, okay, at least 1 cup of coffee per day? Now, let's do this. What's the meaning here of at least 1? This is the key. Now, to have at least 1 cup of coffee, what that means is you have 1 cup or more. So at least 1 means 1 or more. And that's the key. That's the meaning of this phrase here, at least one. So I'm going to go identify here my data values that are at least one. One or more means one or two or three or four. Okay. I'm now going to have to add those associated percentages here for at least one. And that's going to mean I'm going to take this 14.7. I'm going to add it with 17.6. I'm going to add it with another 14.7 and 23.5. Okay, we're going to add all of these and we're going to see what we get. So we get 14.7 plus 17.6 plus 14.7 plus 23.5. That's about 70.5%. So what we can say here, when they say what percent of the sample drinks at least 1 cup of coffee per day, this is about 70.5%. And we found that by simply understanding the concept or the meaning of the phrase, at least one being 1 cup or more, and all of these data values that represents the number of cups of coffee that are in red are at least one. It means 1 is 1, 2 is at least 1 since it's more than 1, 3 is at least 1 since it's more than 1, and so is 4. 4 is at least 1 since it's more than 1. And this is how we answer our question for that part B, I guess. What percent of the sample drinks at least 1 cup? Now, for C, different question. They want to know what percent of the sample, okay, we're going to change that here. What percent drinks, put a colon here. This is at least 1. The next question wants to, or has to do with, more than 1 cup of coffee. So we're going to talk about what more than 1 cup of coffee per day. The key again is to understand the meaning of the phrase more than 1. And more than 1 means greater than 1. Greater than 1. So let's go back here to our data values and consider which data values are greater. To be greater means to be strictly larger than. So I might want to put this down as well. Strictly larger than 1. So which of these data values are strictly larger? Well, 1 is not larger, 1 is the same. 2 is larger. Okay, 3 is larger, and 4 is larger. So the data values that are larger than 1 are 2, 3, and 4. So what we're going to do now is we're going to add those percentages associated with being greater than 1, more than 1, larger than 1. And that's 17.6. So let's write this down. It's going to be 17.6 plus 14.7 plus 23.5. So when I go through and add these values, we're going to end up with 17.6 plus 14.7 plus 23.5. We get 55.8%. So 55.8% of the sample drinks more than 1 cup of coffee in this particular homework question here. Okay, so that's going to be information they ask, more than 1, and that's actually comes from what percent of drinks more than 1 cup. That's part C. Part D, what percent of the sample drinks less than 3 cups? So let's talk about less than 3 cups of coffee, and that is going to be per day. Again, the key is to understand the meaning of the phrase less than 3. Less than 3 means strictly smaller than 3. So I have to go look at the data and consider which data values here are strictly smaller than 3. Smaller than 3. Let's be careful here. Smaller than 3. While 3 is not smaller than 3, it's 3. 2, 1, and 0. These are the data values that are strictly smaller, less than 3. And these are the associated percentages. So we're going to have to add now all of these percentages associated with being having data that's strictly smaller than 3 in terms of drinking cups of coffee. Okay, so let's go back and we get 29.4. Yeah, that's 29.4, sorry. $29.4, 14.7, and 17.6. We're going to add those percentages. We end up with 61.7% of the sample drinks less than 3 cups of coffee per day by adding the associated percentages. No more than 2 cups. So the next question that we're going to have to answer here is what percent, let's write this down, more than 2 cups of coffee per day. Let's double check. Oh, let's go back. Question E is actually not more than 2 cups. No more than 2 cups of coffee per day. No more than 2 cups. Well, no more than 2, ironically, again, the key will be understanding the meaning of that phrase. No more than 2, ironically, is not more than 2. Not more than 2. This really means 2 or less. So not more than 2 means 2 is the max. 2 is the limit. So we're talking 2 or less. Ironically, if I go back and look at my relative frequency table or frequency table that we just created here, not more than 2 is actually, well, let's think. Or 2 is the limit here. 2, let's go back. What I want to say here is that 2 is not more than 2, 1 is not more than 2, and 0 is not more than 2. All of these data values were already considered in the prior question. So what this means here is that all the associated percentages for these data values that are not more than 2, we're going to go back and actually do the same work here. Meaning we're going to have to add 29.4% plus 14.7% plus 17.6%, and we end up with, again, 61.7%. So it's really the same question. The phrase no more than 2 is the same here as less than 3. That sometimes happens. So they just ask the same question in a different way. Not a big deal. It's just that the statement here, less than 3, in this example is the same as no more than 2. Same exact answer. So we can say 61.7% of the sample drink no more than 2 cups of coffee. Let's look at the next question. F, what percent of the sample drinks between 1 and 3 cups? So what percent drink between 1 and 3 cups of coffee between 1 and 3. Okay, let's go back and consider the key being if we understand the phrase between 1 and 3. Now, I want to point out here that this is inclusive. This between phrase is inclusive, meaning we include the 1 and the 3. So when I go back and look at my data values and determine which ones are between 1 and 3, okay, let's be careful. Looks like we lost some data. I think that was 29.4. Okay, 17.6 here, and 14.7 disappeared. Okay, looks like we're good. Let's consider the data values that are between 1 and 3. 1, 2, 3. We include 1 and we include the 3. So we're going to add percentages associated with those data values. 14.7, 17.6, 14.7. So let's go back here. 14.7 plus 17.6 and another 14.7%. So let's go back and add these percentages. And we find out that we get about 47%. So 47% of the sample here drinks between 1 and 3 cups of coffee. And this is how we answer questions on gathering data, creating a frequency table, relative frequency table for question 1 and that Statistics Lecture 1 homework. So here's the questions here and all the answers. Let's take a look now. Let's take in here, if we can, this third question. Question 3 here. We're going to do the same exact thing that we did for question 1, meaning if question 3, how long did you wait in line at the Husky store for your coffee? And this data here is measured in minutes. So let's go back to the data and let's notate that this is going to be a wait time. Wait time in minutes. And that's what our data here represents. Wait time in minutes. How long did we wait for that particular cup of coffee? Let's go back now here and determine the frequency value for the wait time in minutes. Okay, so let's count how many zeros. 1, 2, 3, 4, 5, 6, 7. The frequency of data value 0 is 7. Let's get the frequency for the data value of 1. So if I scroll through this list, I got 1, 2, and I believe there's a comma here. 3 and 4. Let's look at the data value here. Let's double check. 4011. Yeah, there's a comma there. Okay. The data value 2. 1, 2, 3, 4, 5, 6. It looks like there's 6. 6 twos. How many threes? 1, 2, 3, 4. 5 threes. How many fours? 1, 2, 3, 4, 5. 5 fours. And how many fives? 1, 2, 3, 4, and 5. 5 fives. So it looks like if we scroll through again, every single data value is accounted for and is in my table. Again, let's recall. I need the sample size, which is the sum of my frequency values. So if I add all these frequency values here, I'm going to get a sample size. Now let's consider what we have to add. 7 plus 4 plus 6 plus 5 plus 5 plus 5. Let's go back. 7 plus 4 plus 6 plus 5 plus 5 plus 5 gives us 32 data values here. So our sample size here is going to be 32. Let's double check. 7 and 4 is 11 plus 6 is 17. Add another 5, you get a 22, and add another couple of 5s, you do get a 32. Sample size here happens to be 32. So we add our frequencies and we did get the sample size. Relative frequencies. 7 over 32. 4 over 32. 6 over 32. 5 over 32. 5 over 32. And 5 over 32. So each of these relative frequencies we're going to approximate, and I think in question 3 they want us to round to the nearest 10 thousandths. So the nearest 10 thousandths. Alright, let's see what we get here. 7 divided by 32. I get 0.2187. 5. So let's find the position here. This is going to be tenths, 100,000, 10 thousandths. This is a position we have to approximate to. We look at the digit to the right. Since it's a 5, that means to do the following. Add 1 to the 7 and drop your 5. So that now gives me here an 8, and we get approximately 0.2188. And so the first relative frequency will be 0.2188, which is 21.88, and this is percent. Let's find the next relative frequency. 4 divided by 32. Well, that's exactly 1.25. So I'll put exactly 1.25 here, which means I have 12.5%. 6 over 32, relative frequency. This is 0.1875, and this is exact, and we are out 4 decimal places, which is the nearest 10 thousandths. So 6 over 32 we can replace now with 0.1875, which means we have 18.75%. And then finally, 5 over 32. We'll see what this becomes approximately. Is 0.15625. So now here, 10 thousandths. Here's a 5. We add 1 to the 2. Forget about the 5. And this is how we're going to approximate this. This is going to be 0.1563. Okay, so 0.1563. And so, since the others are the same frequency values, 5s, they have the same relative frequency. And as a consequence, the same percentage. So this is 15.63, 15.63. Okay, it looks like here we have the percentages. We're now ready for the questions here. So I'm going to erase all these things here. And we're going to get ready here to start answering the questions here for these homeworks sections here. So these kind of questions. All right, number 3. What percent of the sample waited at least 2 minutes? So at least 2 minutes. So remember, this is wait time. And they want to know what percent waited at least 2 minutes. Again, the key is knowing what at least 2 means. And at least 2 means 2 or more. So I have to find the data values that are at least 2. 2 or more. 2, 3, 4, 5. These are my data values that are at least 2. And then we have the associated percentages here for each of those data values. So we're going to end up here adding the associated percentages, and we get 18.75 plus 15.63 plus 15.63 plus another 15.63. So let's go through here and add the associated percentages. We get 18.75 plus 15.63, another 15.63, and another 15.63. We should get 65.64%. So 65.64% here waited at least 2 minutes for their coffee. Okay, the next question is, what percent of the sample waited for more than 2 minutes in line? So more than 2 minutes. More than 2. Alrighty, let's kind of figure out, again, the key here. So understand the meaning of the phrase more than 2. Now, more than 2 strictly means it is greater. Oops. Let's get this out. Greater than 2. Larger than 2. More than 2, greater than 2. So all I have to do is go back and remove this 2. And all of these data values, 3, 4, or 5, are all more than 2, greater than 2. So we're going to just add the associated percentages here. And the associated percentages are all, notice, 15.63%. So we take that 15.63 plus another 15.63 and another 15.63. We're going to add those together. And we're going to see what you end up with. %46.89%. More than 3, 46.89% of the sample drinks are waited for more than 2 minutes. And let's see what comes next. We got more than 2, less than 5 minutes. Less than 5. So what percent waited less than 5 minutes? Now, less than 5 means, right, again, the key. Less than 5 means, again, strictly smaller than 5. Smaller than 5, let's go back. The data values that are smaller than 5 are certainly 4 and 3, but they're also 2, 1, and 0. These are all the data values that are smaller than 5 or less than 5. So we're going to have to add the associated percentages here. It looks like I lost a 3. We're going to have to add the associated percentages And these are all the associated percentages associated with the phrase less than 5 here. Okay, so there's a lot there. 21.88. Let's go do this. Plus 12.5 plus 18.75 plus 15.63 plus another 15.63. Okay. And let's see what we end up with. 21.88 plus 12.5 plus 18.75 plus 15.63 plus another 15.63. We get 84.39%. 84.39% here of the sample waited for less than 5 minutes. Less than 5 minutes. Okay, what's the next question now? Less than 5. No more than 1 minute. All right, let's go back. I'm sorry. Let's go back here and let's note something important. I want to point out to you on this homework that what we could have done is taken the 100% and simply subtracted this remaining percentage over here. Let's change the color. 15.63%. So if I take 100 and I throw out the outcome there, 56.3%, or sorry, 15.63%. 100 minus 15.63. Let's do this clearly. We end up with 84.37%. Now this would be an acceptable answer as well. Now you may look at these two and say simply that, you know what, they're not the same. And you're right, they're not the same. 84.37 is not the same as 84.39%, but they are approximately the same, because the second here we went and approximated our relative frequencies. All of these values for relative frequencies, well, they're all approximate, and we threw a lot of data and information away. So if I approached it slightly different by taking the 100 minus the 15.63%, which really means taking the complement, you'll see that later, we get approximately the same answer, and you could have approached it either way. It would be fine, because 84.39 is approximately 84.37%. It's a lot more to the story here behind approximations, but nevertheless, you could have done that, and that would have also been perfectly fine too. Okay, now we can go to the next one, which is no more than 1 minute in line. So let's go to the phrase here. No more than 1 minute in line. What percent waited no more than 1? Now, no more than 1 here, let's go back, is short for really not more than 1, which really means 1 or less. 1 or less is not more than 1. So, okay, if we said what percent waited no more than 1 minute, well, that means 1 minute or less. Just be careful what we erase, and highlight those percentages associated with no more than 1. No more than 1, 1 or less. So it's 21.88 and 12.5. 21.88 plus 12.5. Gives us 34.38 So 34.38% of the sample waited no more than 1 minute in line. This is how we go about answering that question. Okay, the next one, between 2 and 4. What percent of the sample waited between 2 and 4 minutes? Now, this, again, the key, between 2 and 4, and let's remember that they mean to include, inclusive, 2 and 4, to include 2 and 4. So we go back to include 2 and 4. To be inclusive, 2, 3, and 4. Okay, yeah, 2 and 4. There we go. We need the associated percentages again. Okay. 2, 3, and 4. 18.75 plus some 15 6/3s. We get approximately 50.01%. So about half of the sample waited between 2 and 4 minutes. Okay. This is how you answer these questions for question 3 on the homework. What I'm going to do now here, this is question 3. I'm actually going to skip question 5. Okay. And I'm going straight to question number 7 because it's a little different. It's going to take some time here. So question 7 here, and go straight to 7. I realize I did skip some, but that's okay. Okay, you guys can finish this off yourself. And let's go take a look at question 7 here and go into some detail with question number 7. Question 7, this data is how many semesters did it take you to transfer? Okay. This is the number of semesters. Now, this is organized in bins. So your data here is organized in bins. Again, this is completely made up sample information. It's an exercise. Didn't gather data. But if we try to organize our data into these bins like we did prior, because our bins here consist of a range of data, this is a lot more difficult than you realize, meaning you do have to keep a tally. So just like was demonstrated in lecture, we went through these tallies and we're organizing our data now. We're going to do the same here because notice our data is organized here in bins. So that is a big deal. Okay. Question 7, data organized in bins. So let's go through this exercise like we did prior. And again, we call these bins or classes or whatever, groups. I like the phrase bin. So we're going to determine what bin the data value 4 belongs, and that's the first bin. A 6 goes in the second bin. Okay. 8 lives in the third bin. So we're going to have to do this process for all of these data values. A 4 first bin, a 4 first bin, a 5 first bin, another 5. That's a diagonal. That means there's 5 data values. A 4 and a 5, 2 more. A 6, a 7, a 6, a 7. There's the diagonal again. A data value 8, third bin. 10, fourth bin. A couple of 4s. 1, 2. A 7. Second bin. An 8. Third bin. A 5. Dash. Diagonal. A 4. Another 5. A 10. Fourth bin. A 12. Last bin. 10. Looks like a fourth bin. 1, 2, 3. So first bin, second bin, third, fourth, fifth bin. So the 10 we put in the fourth bin. And there's 4 of those. 4. Let's go back. Let's double check. See, easy to get distracted. We got 1. Let's do this here. A 10, a 10, a 10. 3 10s. 3 dashes. Okay. 8. Third bin. Another 8. Diagonal. 9. Couple of 6s. A 12. A 5. A 4. And another 5. A 6. And a 5. Another 5. A 6. An 8. 7. Couple of 8s. And a 7. 1, 2, 3 9s. 1, 2, 3. A 4 and a 5. A 6. A 12. An 11. A 12. Another 11. A 10. An 8. A 6. A 7. A 4. Couple of 5s. A 4. A 7. An 8. 3 9s. 1, 2, 3 9s. 5, 4, 5. There's 3. 1, 2, 3. A 6. A 5. A 6. Another 6. An 8. A 10. A 5. A 4. A 4. And then a 5 there. Okay. These are our tally marks. Hopefully we didn't make a mistake. We went through this. Now let's determine the frequency. Now each group here stands for 5, 10, 15, 20, 25, 30. Looks like that frequency is 31. 5, 10, 15 plus 4, 19. 5, 10, 15 plus 3, 18. 5 plus 2, that's a 7. And then finally, we got a 4 here. Okay, this looks like we're going to complete here. This every value here was accounted for. Let's see what the sample size is. Again, sample size is some of the frequencies. So if I go back now and I add all of these frequency values, I'm going to get my sample size. So sample size here is going to be 31 and 19 is 50, plus 18 is 68, plus 7 is 75, plus 4, Looks like we had 79 data values. 79. So I'm going to have to now compute here relative frequencies. So this is 31 out of 79, 19 out of 79, 18 out of 79, 7 out of 79, and then 4 out of 79. So we're going to have to compute all these relative frequencies, and then they want us to approximate again to the nearest 10 thousandths. Let's write that down. The nearest 10 thousandths. That's, let's check, tenths, hundredths, thousands, 4 decimal places. Okay. So this is our gathering data here in our bins. Okay, let's see what happens now for this. Let's do this. 31 divided by 79. Okay, so we get 31 divided by 79 is approximately 0.3924. So look at the fourth decimal, or I should say, we're going to approximate to the fourth decimal there. And we look at the digit to the right, which is a 0. And that means leave it alone. 39.24 is our relative frequency. Let's go back. 39.2, oops. Sorry. 0.3924. Let's do that there. 39.24% then. That's what we got. Now let's look at 19 out of 79. So 19 out of 79 gives you 0.24050. The 5 is in the 10 thousandths position. We look at the digit to the right and we get 2405. Okay, let's erase this. 0.2405, which means 24.05%. Remember, this is our percent. 18 now. 18 out of 79. So 18 out of 79, we get 0.22784. This is the 8. Look at the digit to the right. Get rid of the 4. That's 2278. So 2278. .78%. 7 out of 79. We get 0.08860. 1, 2, 3. So the 6 is in the 10 thousandths position. Your 0's to the right. That means get rid of it. 0.0886. 0.886. Okay, this is 8.86%. And then 4 out of 79. Let's see what this gives us. And then we end up with 0.05063. 1, 2, 3. 6 is in the 10 thousandths position. Look at the 3. 0506, 0506, and 5.06%. We now have our relative frequencies. So let's get rid of all of these decimals so we can use this space here to start to answer some of these questions here. Okay. And by the way, let me go back for a brief moment to discuss something important about this. If you do look at, by the way, the question here in A is to construct a frequency table using a bin width of 2 and the first bin having a lower bin limit of 4. Now let's remember bin width. The bin width here is the difference between adjacent lower class limits. So what I want to go back and remind you is that the bin width in this problem here, how they started off this question. That's the difference between 6 and 4, which is 2. So your bin width is the difference between adjacent lower class limits, or we can say adjacent upper class limits, 5 and 7. That difference is also 2. So be very careful here. Okay, here's how we got our bin width. And then they said make sure you start with the first bin having a lower bin limit of 4. So I can go back and say to you, pay attention to the fact that that first bin limit here, by the way, let's go back. The first bin limit did start with a 4, and then it had, again, emphasized that the bin width was 2. So what you can do is start with 4 and then keep adding 2. 4 plus 2 is 6, plus 2 is 8, plus 2 is 10, plus 2 is 12. And what you did was you generated all the lower bin limits. Okay? Notice again, the upper bin limits, all 5, 7, 9, 11, and 13, all differ by 2 as well. So when you started this question and they said construct a frequency table using a bin width of 2, we did right here, bin width of 2, and the first bin having the lower bin limit of 4. You have to know those definitions in order to create this particular frequency table we did. So this is gathering data and going through this in terms of its description of how to organize these tables. So let's now be careful here, and when we go back, let's now start to answer these questions. But that's how we organize this by the instructions given in number 7. Okay. Anything else that you have is just not correct. And assuming we put our appropriate data in the right bins. And okay, now let's go back and answer some of these questions here. The questions are going to be, what percent of the sample took at least 6 semesters to transfer? Okay, at least 6. At least 6 is really code for 6 or more. So you need 6 or more semesters here. So I got to go back and determine here for the bins that we have, which bins hold data values that consist of 6 or more. Bins 2, bins 3, 4, and 5. All those data values hold, or I should say all those bins, the second, third, fourth, and fifth bin, hold data values that consist of 6 or more, meaning the value 6 or 7 or 8 or 9 or 10 or 11 or 12 or 13. So we're going to add the associated, as you guys can guess, percentages associated with this. So here we go. We get 24.05. Let me go back at this color here. I know it's weird, but got to be consistent here. 24.05. Okay. 24.05 plus 22.78 plus 8.86 plus 5.06. Okay, let's see what our calculator says. 24.05 plus 22.78 plus 8.86 plus 5.06, and we end up getting 60.75%. So 60.75% of the sample here took at least 6 semesters to transfer based on this data. Okay. Next question. What percent of the sample took at least 10 semesters? So at least 10 semesters to transfer. At least 10, let's go back and look at our bin situation and determine which bins hold data values that are at least 10. And again, the key here would be to consider the meaning of at least 10. At least 10 means 10 or what? 10 or more. So, which bins hold data values that are 10 or more? 10 or 11 or 12 or 13? Well, it looks like it's bin 3 and bin 4. So we're going to now go back and I think that was 2405. There we go. There's a 0 there. We're going to add 8.86 and 5.06. 8.86 plus 5.06. And that's going to give us 13.92%. 13.92% take at least 10 semesters to transfer based on this table. And then the next question is no more than 9 semesters to transfer. No more than 9. Again, what does this mean? Not more than 9. 9 or less. No more than 9. 9 or less. So if we go back here and try to find the bins that hold 9 or less, bins 3, 2, and 1. Those bins hold data values that are 9 or less. Okay, let's get rid of here. Let's highlight the associated percentages that hold data values that are 9 or less. So here's what we're going to get. 22.78 plus 24.05 39.24. We get 86.07%. So 86.07% of this sample took no more than 9 semesters to transfer. No more than 9. Next question. What percent of the sample took more than 9 semesters to transfer? More than 9. Now this is a complement, really. We'll learn what that means in the future. More than 9, again, let's go back. More than 9 really means, if I thought about this phrase, that's the key, that's greater, larger than 9. Larger than 9, greater than 9. That means 10, 11, 12, and 13. The last 2 bins here. So let's highlight all the bins associated with more than 9. Yeah, I guess let's be consistent. 10, 11, 12, and 13. Those are more than 9. So we're going to add 8.86 and 5.06. And finally end up with 13.92%. 13.92% of the sample took more than 9 semesters. Okay. Next question. less than 10 semesters. All right, let's see what that looks like. Less than 10 semesters to transfer. Let's just leave it at that. Let's be neat. Less than 10 semesters to transfer. Less than 10 again means, the key here means smaller than 10. So let's go back and find smaller than 10. Smaller than 10. The bins that hold data values that are smaller than 10, less than 10, 9, 8, 7, 6, 5, and 4. So it's the first three bins, and we'll highlight the associated percentages with those bins. So if we actually add these values now, 39.24 with 24.05, $22.78. We get 86.07%. So 86.07% of the students took less than 10 semesters. That happens to be the same as no more than 9 semesters. So this is less than 10 semesters. And finally, what percent took between 6 and 11 semesters? Okay. Again, the key here is between 6 and 11. That means inclusive. Right? We include 6 and 11. So which here bins hold between the data values 6 and 11? Let's go back. Between 6 and 11. Bins 2, 3, and 4. $24.05. $22.78. And 8.86. So let's add these. 24.05 plus 22.78 plus 8.86. And we end up with 55.69. 55.69%. 55.69% of the sample took between 6 and 11 semesters to transfer. And this concludes question 7. So if I look now and try to import the information for the last question, or I should say question 9, let's at least go over some of this. And say that they want us to construct these frequency tables using a bin width of 12. So my bin width is 12. And they want the first bin having a lower bin limit. This is now for the first bin, having an LBL, lower bin limit, of 50. So what this means here, again, is this. I start with 50. That's my first bin. That's the lower bin limit. And now I have a bin width of 12, so I get the other lower bin limits by adding 12. 50 plus 12 is 62. 62 plus 12 is 74. 74 plus 12 is 86, and 86 plus 12 is 98. These are now my adjacent lower bin limits using a bin width of 12. Now, how I get the upper bin limits for the bins would be the following. 1 less than 62 is 61, so I'm going to start with 61. Then I use again the bin width of 12 and add 12. 61 plus 12 is 73, plus 12 is 85, plus 12 is 97, plus 12 is 109. So I'm using the bin width of 12 to create these bins. Now let's go through the data here and let's organize or tally this data. I got a 50, first bin. 52, first bin. 65, second bin. 78, third. Let's label this first, second, and third, fourth, fifth. 88, 94, 55, 69, 70, 72, 55, 74, 100, 88, 90, 95, 65, 82, 55, 66, 72, 84, 88, 102, 96, 98, 102, 88, 56, 79, 52, 106, 108, 100, 96, 99, 102, 108, 56, 73, 55, 66, 87, 67, 74, 87, 90, 92, 99, 78, 83, 108, 101, 95, 83, 104, 68, 60, 79, 70, 88, 100, 95, 77, 80, 95, 75, 65, 55, 90, 78, 84, 66, and 92. Let's look at these frequencies. Again, we get 5, 10 plus 1 is 11. 5, 10 plus 4, 14. 5, 10, 15. 5, 10, 15 plus 4 is 19. Again, 5, 10, 5 is 15. Again, sample size is the sum of the frequencies. So I'm going to add all my frequency values to get a sample size. So 11 and 14 is 25 plus 15 is 40. 40 plus 19, 59. 59 plus 15 is 74. Looks like my sample size here is N is 74. Let's write this down nicer. Okay, so 11, 14, 25, 40, 59, 69, 74. Okay. So let's compute this here. 11 out of 74, 14 out of 74, 15 out of 74, 19 out of 74, and then 15 out of 74 again. Okay. 11 out of 74. So they want us now, let's go back and say to you that they want us to approximate this to the nearest thousand. So that's 3 decimal places. So I have 0.1486. So this 8, 3 decimal places. Approximate your relative frequency to the nearest thousands. The 6 means I have to add 1 to the 8, and so we get approximately, okay, 0.149. 0.149. 14.9. Again, these are percents. 14 out of 74. 0.1891. So that 1 says leave the 9 alone and you're gone. So approximately 0.189, 0.189, 18.9%. 15 out of 74. 0.2027. The 2 and the 7, this means add 1. So that should be approximately 203. 0.203, 20.3%. 19 over 74. 0.25, 0.2567. The 6 is in the thousands position. Look at the 7. Add your 1. So we're going to get this to be approximately, let's see, 0.266. 0.266. 26.6%. 15 out of 74. 0.2027. 2 is in this position. We're going to add 1. So you have here 0.203. 0.203. 20.3%. So this is how we've organized our bins here. 14.9%, 18.9%, 20.3%, 26.6%, and 20.3% here. Okay, let's erase all this so that we can start to answer those questions. Okay. What percent of the sample has at least 62? At least 62. Okay. At least 62 friends. So remember that this data that they gathered, they're trying to find out, this is the number of Facebook friends. So you're counting the number of Facebook friends that you have, and what percent of the sample has at least 62 Facebook friends. So at least 52 Facebook friends. So 62 or more, remember, let's go back, and the key phrase here for at least 62, that means 62 or more. Second bin, third bin, fourth bin, fifth bin. So 18.9 plus 20.3 plus 26.6 plus 20.3. So if we add the associated percentages here, let's see what we end up with. %86.1%. Okay, at least 62, 86.1%. So 86.1% of the sample has at least 62 friends on Facebook. No more than 85 friends. Next question, what percent of the sample has more than 85 friends on Facebook? More than 85. More than 85 here. (86 to 109). Bins 4 and 5 hold data values that are more than 85. So we're going to take 26.6 and add it with 20.3. 26.6 added with 20.3. And that looks like it's going to give us 46.9%. Remember, more than 85, just to go back, you're looking at greater than what? Greater than 85. More than 85. 46.9%. No more than 85 friends. No more than 85. Again, the key here is to identify and recognize the meaning of no more than 85. Now that's short for not more than 85, or simply 85 or less. So 85 or less, no more than 85. Let's go back. Those are bins 1, 2, and 3. 85 or less. So 1, 2, and 3. First three bins hold data values that are 85 or less. Now, take 14.9 plus 18.9 plus 20.3. So I can add this. We simply end up with 56.1%. So 56.1% have no more than 85 friends on Facebook. The next phrase, at least 86 friends. At least 86 friends, again, the meaning of at least 86 simply means 86 or more. So let's go back to the bins that hold data values that are 86 or more. Okay. Bin 4, bin 5. So for bins 4 and 5, we get 26.6 and 20.3. That looks familiar. Yeah. Oh, more than 85? Yep, here it is, 46.9. So we have 26.6 plus 20.3 will give us 46.9%. Okay. 46.9% of the sample has at least 86 friends. And then let's look at the phrase less than 74 friends on Facebook. Less than 74. Again, if you know the meaning of less than 74, that means smaller than what? 74. So let's go look at the bins that hold data values that are smaller than 74. Bin 2, bin 3 holds data values that are smaller than 74. So okay, all these data values 50 to 73 are smaller than 74, so we're going to take the associated percentages of 14.9 and 18.9. So 14.9 plus 18.9, and we get 14.9 plus 18.9 gives us 33.8%. 33.8% of the sample has less than 74 friends on Facebook. And then finally, between 62 and 97 friends on Facebook. Remember, the key is always to know the meaning of these phrases and inclusive. This means include 62 and 97. So let's go back at the bins here and find which ones hold what we need, meaning they have to be between 62 and 97. Second bin, third bin, fourth bin. We're going to add the percentages associated with those particular bins. Second, third, fourth. 18.9, 20.3. And 26.6. We get 65.8%. 65.8% of the sample hold between 62 and 97 I should say 65.8% of the sample have between 62 and 97 friends on Facebook. And that concludes the homework for this worksheet.